In my presentation, I will talk about scale-related methods for saddle point problems. Recently, many researchers actively working in the subjects of scale-related methods for saddle point problems based on their structures. In this direction and in this subjects, there are more and more works. In this slide, we mentioned 2 or 3 works in this year. In this work, we consider the following saddle point problem, where Qx and Qy are convex sets. The function R is mu x strongly convex. The function h is mu y strongly convex. The function fxy is convex by x and concave by y. We consider the case when the function fxy is sufficiently smooth, which is mean that this function satisfies the following smoothness conditions for some real positive reals lxx, lxy, and lyy. From the point of view of this, of the considered saddle point problems and scale-related methods for the class of problems, the case special case when the function fxy has a bilinear structure. This case is sufficiently studied by Lan in his works. In our work, we consider the general case of the saddle point problem in which the function fxy not necessarily bilinear. And we show under rather general conditions that the best known bounds for bilinear convex concave saddle point smooth composite saddle point problems keep true for non-bilinear convex concave smooth composite saddle point problem. Let we see now some of these bounds. Denote by S hat to the difference between the function fxy and the function h. Jx is the maximum of this function. Since the function h is mu y strongly convex, the following maximization problem has a unique solution. By these denotes, we can rewrite the considered saddle point problem as follows, which is the minimization problem, composite minimization problem. As we say that since this maximization problem has unique solution due to the strongly convexity of this function, therefore we can use the scale-related gradient descent method in order to solve this problem, and as a result we have the following complexity. For the function Jx in this problem for this function, in any arbitrary point there exists ellipsis gradient, where L has the following form: Lxx plus 2Lxy square over mu y. And therefore this minimization problem, which is mu x strongly convex, smooth composite optimization problem, we can use the scale-related gradient descent with delta L oracle, delta L gradient. This concept was considered and studied in De Volder's work. Therefore, for this problem, we can use strongly convex smooth composite optimization problem. We can use the technique of restarts of a scale-related gradient descent method. This is a scale-related gradient descent method with delta L gradient for composite optimization problem. We can use the technique of restarts of this algorithm, which is present in this algorithm, in order to solve this problem. And as a result of using the technique of restarts of this algorithm, we have the following complexities. We have the following complexity, and due to the L is equal to Lxx plus 2 Lxy squared over mu y, we have the following complexity in order to solving the external problem in our concave saddle point problem. In order to solve the internal maximization problem. Internal, this is a maximization problem. In order to solve this problem by the technique of restarts, we have the following complexity. In order to compare these complexities with other complexities, we compare with the complexities of mirror-approx method. This method is very famous and popular in order to solve convex concave saddle point problems and variational inequality problems. This method was proposed by Arkady Nemirovsky in 1924 in this work. By using the mirror-approx method, we have the following complexity. This complexity, in the case if mu x or mu y is very small, the required number of iterations may turn out to be quite large. But by accelerated method, we have the following complexity. This complexity is better than the previous in the case when mu x is more and more less than mu y, or mu y is more and more less than mu x. As a special case of considered saddle point problem, we consider the following classical optimization problem with one functional constraint. In this optimization problem, there's assumptions. F is mu strongly convex, the functional of constraints is simply convex, not necessarily strongly convex. If we introduce the dual factor, then this problem we can rewrite as follows. This is a dual problem to this proposed, to the considered problem, optimization problem. And for this problem, in order to solve this problem, in this work, it was considered the following algorithm, which is listed in this slide as algorithm 3. In this algorithm, in third item, we use the method dichotomy, and in the fourth item, we solve auxiliary minimization problem, one-dimensional auxiliary minimization problem. This is a one-dimensional optimization problem. This algorithm is adaptive. The stopping criterion of this algorithm is adaptive. And as a result, under the assumptions when the objective function and the functional of constraints are smooth, we have the following complexity, and under the assumptions when the objective function and the functional of constraints are non-smooth, we have the following complexity. This complexity is generally not optimal, but practically in practice, it seems that this proposed algorithm works better than optimal ones, such as mirror descent method. We consider two examples in numerical experiments. This is the first one. Objective functions has the following form, and the example, in the second example, we consider this function. The functional constraint is the maximum of 100 quadratic functionals, and we have the following results. The running time of compared algorithms as a functions of 1 over epsilon. Epsilon is the accuracy of the solution. As we can see from these results, the proposed algorithm, which is listed as algorithm 3, which is not optimal in generally, works better than other optimal adaptive mirror descent method. And in this algorithm, there is no need or knowing any information about the strong convexity parameter. Unlike in the adaptive mirror descent methods, we require the strong convexity or to the objective functions and the functional of constraints, which is in this algorithm, algorithm 3. We require the strong convexity only on the only of the objective functions. This is the presentation. Thank you so much.
So again, we have plenty of time for questions. So if you have questions.
Yeah. I can try that. Like the main purpose of this algorithm was to like introduce this non-dependency of strongly convex of strong convexity parameter.
Yeah, this work, there's two parts in this presentation. The general part, the first part is for the general case of the saddle point problem. In this part, there's no, the goal is the study the accelerated methods in order to solve these problems in the general case when the function f is non-bilinear. There are a lot of works in George Lan book about this problem when the function f is bilinear. This is the first part. The second part is this. In this paper, there were considered two algorithms. There is one of these algorithms. This algorithm was proposed in order to solve this optimization problem. The efficiency of this algorithm is at the first, there's no knowing adaptive algorithm. There's no needing to know any information about the strongly convexity parameter, any information about the parameter of smoothness. If the objective function is if the objective function is smooth, this is unlike in the optimal methods, adaptive mirror descent method. In this algorithm, we need knowing the strongly convexity parameter mu. Yeah.
Okay, and considering the experiments, did you assume that you know the strong convexity parameters for the problem?
Yeah. Because in this we did a comparison between mirror descent methods and the proposed algorithm listed as algorithm 3. In this algorithm, there is no need to know this parameter, but in this algorithm, we must need the convexity parameter. But therefore, we consider these quadratic objective functions. This is quadratic objective functions, and we can easily know the convexity parameter. And in this is strongly convex with the parameter is equal to 1. Yeah.
Okay, and is it somehow possible to combine these two algorithms? I mean, the theoretically optimal one and the one that was proposed in your work to.
I don't know if there exists. No,